Welcome to part 4 of this series of data fitting. In this part we look at the exponential models, growth, decay, and the important concept of half-life. Exponential models describe things that grow or decay at rates proportional to their current value. The growth equation is y equals a times e to the power of bx, and in this case b is greater than 0. Here e is approximately 2.718, which is the Euler's number. The letter a is your starting value, and b is the growth rate. Watch exponential growth in action, as you can see here in this figure. This gives a curve that starts slow, but it accelerates dramatically. So it's a classical J-shaped growth. There are many examples of this kind of curve, but I can give you some of them. For example, bacterial populations as they grow, and there is in financial applications compound interest, and in biology viral spread. So the idea behind all of these phenomena that things can get very big and very fast. For decay, we just make the exponent negative. So in this case, y equals a times e to the power of minus bx. Now the curve starts high and decreases, and it will approach 0, but it will never quite reach 0. And again, there are examples of this phenomena or this kind of curves, and these include radioactive decay, and in pharmacology the process of drug elimination, and also in material science the process of cooling of hot objects, which follow Newton's law of cooling. Exponential decay is everywhere in science. The key feature is that a constant fraction disappears in each time period, so it's not a constant amount. So watch how the concentration drops rapidly at first. When the decline slows down, it keeps halving, so it will get to half of the original amount, getting closer to 0. But as mentioned before, it will never get to 0. So it always get closer to it, but never gets actually to the actual value of 0. Half-life is the time for half the material to remain. It's calculated using the equation T half equals 0.693 divided by B. And you could express that in a different format, natural log of 2 divided by B. And this calculation, or this kind of this equation of half-life, is very important and has very important applications. So I can give you example here. A drug with B value equals to 0.1 per hour has a half-life of about 7 hours. Also, when for example dating materials, carbon 14 has a half-life of about 5,730 years. So the beauty of this value, half-life is a constant value regardless of how much you start with. So that is the signature of exponential decay. Let's look into this and model bacterial growth. So you will notice that population doubles exponentially. The doubling time equals the natural log of 2 divided by k. K is a constant. So larger k means faster growth. This same mathematics applied to other applications in finance as explained earlier on, like compound interest. So basically money growing exponentially in your savings account. In pharmacokinetics, we can find another example. So in this case, it will explain how drugs move throughout the body. So it will heavily follows exponential decay. This is what we call first order pharmacokinetics. The half-life is T half equals 0.693 divided by the K constant. This determines the therapeutic window which we explained before, and that is the range where a drug concentration is effective but is not toxic. So understanding half-life guides dosing regimens. How often patients need to take their medications. So this is heavily based on the calculations used or based on half-life. The Arrhenius equation is a powerful exponential model used to predict the temperature dependence of chemical degradation and ultimately pharmaceutical stability. The challenge in drug development is that shelf life may be years, but decisions must be made quickly instead of waiting. So in this case, degradation is measured over short time at elevated temperatures, and the results can then be extrapolated to normal storage conditions. As you can see here, this is the formula for the Arrhenius equation as shown here on top. So the relationship here is clearly showing the K, which is the rate constant, A is the pre-exponential factor, EA is activation energy, R is the gas constant, and T is the absolute temperature. So if you plot the values as can be shown here, you'll end up with the activation energy, where that is the slope, which is negative or minus activation energy divided by the R gas constant. Remember, we've covered the Kissinger method early on, and this is to understand the correlation. The activation energy here can be obtained either from isothermal Arrhenius stability studies or independently from non-isothermal DSC data using the Kissinger method. So what does that mean? When we say non-isothermal DSC data, means we're gonna heat the sample as you've seen early on, and we use Kissinger method because that provides a rapid assessment of the activation energy early in the development process of pharmaceutical formulations, which can then be inserted into the Arrhenius equation to predict the degradation rate at storage temperature. So the beauty of this, using a linear fitting, it converts an exponential relationship into a straight line, making parameter estimation straightforward and robust. And that assumes that the degradation mechanism does not change with temperature.